So, good morning everyone. So, today we have our next lecture, lecture number 3, based on region of convergence of Laplace transform. And this topic belongs to the course that is Basic Signals and Systems, which has a code BEE303, and this is intended for EN students which are from second year. So, in the last lecture, what we have studied about only the Laplace transform definition and equation of the Laplace transform, how to find out the Laplace transform by integrating minus infinity to infinity xt e to the power minus st dt, we can have the value of the x's. So, in this lecture, we see what is region of convergence of the Laplace transform, that is ROC of the Laplace transform, and how it is essential to review the Laplace transform in a detailed form. So, what we have the region of convergence for the Laplace transform. So, you can see from the figures that there are some figures in which there is real of s in the x-axis and imaginary of s in the y-axis. So, basically ROC is the formation of real of s and imaginary of s. Why it is so? Because in the last lecture we have done xs is equivalent to minus infinity to infinity xt e to the power minus st dt. So, this s, small s, comprises of sigma plus j omega. Here sigma is real part of s and j omega is imaginary part of s. So, from the figure we have drawn real of s and imaginary of s. Real of s in the x-axis, in the x direction, and in the y direction we have imaginary of s. Also, the ROC comprises of two planes. One is right half plane, this one, and the next one is the left half plane. So, suppose let R denote a set in the complex plane, a set R comprised of all complex number s such that real of s is less than a. So, the first figure, that is A figure, denotes real of s less than a. So, here there is a pole which is at A, and we have drawn a dotted line just parallel to the imaginary of s, and the portion which is real of s less than a is the ROC region. So, this is particularly the ROC region. So, this comprises of the left half plane, because from the pole we are considering the left half of the ROC region. Similarly, we have real of s less than a if the pole A exists in the right side. Suppose this is 0. So, in the first case A is less than 0, and in the second case A is greater than 0. But in both the cases we have real of s less than a, because the ROC is in the left half plane. So, here also real of s less than a. Similarly, if real of s greater than a, so this is for real of s greater than a. So, in this case the ROC is the right half plane, this is the right half plane, and first we have taken when a is less than 0, and the second is taken when a is greater than 0. But in both the case we have real of s greater than a. So, we have two kinds of ROCs here. First one is real of s less than a, which shows the left half plane, and the second one is the real of s greater than a, which shows the right half plane. So, when there is only one pole. So, there is some properties of the ROCs. The first property, the ROC of the Laplace transform X consists of strips parallel to the imaginary axis. As we have seen here, the ROC is the strip which is consisting strip which is parallel to the imaginary axis in the complex planes. So, that is, if S is in the ROC, then S is equivalent to S plus j omega is in the ROC for all omega. So, here this should be sigma, S is equivalent to sigma here. So, in the first figure we have two strips which is a valid ROC, that is, suppose it is minus 2 and this is 3. So, here it is real of S greater than minus 2 and less than 3. In the second one it is also valid, suppose it is minus 1 and this is real of S greater than minus 1. In the third, this is not a proper ROC definition or the ROC region, because the strips are parallel to the x-axis. Always the strips are parallel to the y-axis in the case of ROC. So this is invalid type of ROC. The second property is if the Laplace transform x is a rational function, then the ROC does not contain any poles and the ROC is bounded by poles or extends to infinity. Since x is rational, its value becomes infinite at pole. So obviously x does not converge at a pole, therefore it follows that the ROC cannot contain a pole. So if there is some rational or imaginary part occurs in the case of the ROC or the x's. So suppose x's has some imaginary values in the denominator. So this is suppose s plus 2j, like this, 2 upon s plus 2j. So in this case there is no real part in the case of poles. So the poles exist at 2j or suppose s plus 2j and s minus 2j. So there is s plus 2j and this is s minus 2j. So in this case the ROC will not be containing any pole because the poles are on the imaginary axis. The poles must lie on the real axis for having some ROC of the Laplace transform. In the second case, in the first case it is valid because there is one pole existing in the real axis. In the second case both the poles are on the imaginary axis. That's why it is not valid. It's not valid, or we have to write it real of s greater than 0 in this case. In the third case it is invalid because there are two poles on the y-axis, or there is a strip line which is having there is no real of s greater than no any value here and less than there is not any value here. So there is no any value greater than or less than, that's why it is invalid type of ROC. The third property, if a function x is finite or finite duration and its Laplace transform x converges for some value of s, then x converges for all values of s. Then the ROC is the entire complex plane. For example, when you find the Laplace transform of ut, so when you find out the Laplace transform of ut, it will be minus infinity to infinity xt e to the power minus st and dt. Or if you find out, in this case you will have 0 to infinity ut 1 into e to the power minus st and dt. So in this case it is 1 upon s. But in the case of here also real of s greater than 0 is the ROC. Not the entire plane, but in the case of xt is equivalent to del t, which is an impulse function. So in this case xs is minus infinity to infinity del t e to the power minus st and dt. As we know the property minus infinity to infinity del t dt is equivalent to 1. So in that case we have e to the power minus st at t equivalent to 0, and this value becomes 1 when t equivalent to 0, as we know the property, that is minus infinity to infinity del t dt. This is 1 when t equivalent to 0. So when you put t equivalent to 0, e to the power minus st becomes 1. So here there is no, in this case there is a denominator term which is s. So we can write real of s greater than 0, as this is a right sided signal because of this ut. But in this case there is no denominator term, we have only an integer value, that is 1. So we don't have any kind of restrictions to the poles, or all the poles, or you can have the entire S plane will be the ROC for this particular case, that is xt is equivalent to del t. So in this case the ROC is the entire S plane. Okay. So next property, property number 4, if a function x is right sided and the vertical line real of s is equivalent to sigma naught is in the ROC of the Laplace transform x of x, then all values of s for which real of s greater than sigma naught must also be in the ROC. That is, the ROC includes a right half plane containing real of s is equivalent to sigma naught. Moreover, if x is right sided but not left sided, the ROC x is a right half plane. So beautifully you can see from the graphs also. In the first case we have, suppose there is some value minus 2. So here it is real of s greater than minus 2, which is a valid ROC and it shows the right half plane. In the second case, it is invalid because it is showing the left half plane. So here the ROC is real of S less than 2. In the third case, it is also invalid because it consists of both the planes. One is right sided and one is left sided. So this is real of S greater than minus 2 and less than 2. But we have values that is real of S greater than sigma naught. So for this case, we have a valid ROC, this. So there are some properties of the Laplace transform. So firstly, we have to see the one thing, 1 minute, sorry. So we have done fourth property, and then similarly the fifth property, that is if a function x is left sided and the vertical line real of s is equivalent to sigma naught is in the ROC of the Laplace transform of x, then all values of s for which real of s less than sigma naught must also be in the ROC. Then the ROC includes the left half plane containing real of s equivalent to sigma naught. So in this figure you can see first one is the valid ROC because it is real of s less than some value of sigma naught, and the second one is invalid because it consists of both the planes, that is the right and left, and the third one is also invalid for this case because it consists of only the right half plane. So the sixth property, if a function x is two-sided and the vertical line real of s is equivalent to sigma naught is in the ROC of the Laplace transform. If the function is of two-sided, then the first one is the valid ROC, suppose it is minus 1 and 1 and this is 0. So we write here real of s greater than minus 1 and less than 1, which is the valid ROC. The second one is not for the two-sided case because it consists of only one pole. So it's an invalid ROC and it has only right half plane. Similarly, the third one which does not contain any pole and it is the entire S plane. So this is also not a valid ROC for a case of two-sided signal or a bilateral Laplace transform. So seventh property, the Laplace transform x of a function x is rational, then small x is right sided, the ROC of x is to the right of the rightmost pole of the x, and if x is left sided, agar signal ही आपका left sided है, then we have the ROC of x to the left of the leftmost pole of the x. So this is a simple thing that if xt, for example, xt is equivalent to ut, in this case right of the rightmost pole will be the ROC, or you have suppose ut minus 2. For this case, real of s greater than 2 because it has a pole, or because it does not mean this, sorry. So we do not have this. So this is the right of the rightmost. For this case, right of the rightmost pole will be the ROC. And similarly, for xt is equivalent to minus of or plus of u of minus t. For this case, minus 1 upon s will be the xs. Xs is equivalent to minus 1 upon s. So in this case, we have xs is equivalent to 1 upon s. So here ROC is real of s greater than 0 and here ROC is real of s less than 0. Both the case, this is right half plane and this is left half plane. Suppose there are two poles existing, which is here is minus 2 and here is 3 and the dotted lines. This is real of s and this is imaginary of s, and we have for both the cases we have the right of the rightmost, both the signals are for the right sided signal. So the right of the rightmost pole will be the real of s greater than 3. Similarly, for left of the leftmost pole we have real of s less than minus 2. So this is for left of the leftmost pole, this portion, and for the right of the rightmost pole, this portion. For this we have this. So example 1, the Laplace transform x of the function small x has the algebraic expression. Identify all the possible ROCs of x, for which each ROC indicate whether the corresponding function x is left sided but not right sided, right sided but not left sided, or finite duration. Identify all the possible ROCs of x, for each ROC indicate whether the corresponding function is x is left sided but not right sided. So we have xs is equivalent to s plus 1 by 2 upon s square plus 2s plus 2 upon multiplied by s square plus s minus 2. So when we solve here, we have the possible poles of this function is s plus 1 by 2, because in the upper part we have s plus 1 by 2 which consists of which shows the zeros. So we have 1 0 at s equivalent to minus 1 by 2, and poles we have at minus 2 1, because s plus 2 s minus 1, and also minus 1 plus j and minus 1 minus j. So we have these type of poles existing in the case. So we have the ROCs, that is, if you draw, so one is minus 2, one is 1, again minus 1 plus j. So it has a pole which existing on minus 1 also. So we have a minus 1 thing also. So there are 3 poles existing, and obviously in this portion we have complex values. So we have real of s less than minus 2 if all the poles are on the left sided, real of s greater than 1, real of s greater than minus 1 and less than 1, and real of s greater than minus 2 and less than minus 1. So these are some possible ROCs for this particular question. So you can see from the figure also. So there are some properties of the Laplace transform. So these properties are very important to solve numerous kind of questions based on properties. So the first property is linearity property. Linearity property is basically, we have already discussed, follows both the homogeneity and superposition principle. So if there is a signal x1t which has a Laplace transform x1s, another signal is x2t which has a Laplace transform of x2s, then a1 x1t plus a2 x2t has a Laplace transform of a1 x1s plus a2 x2s. So this is basically linearity property. The summing part is superposition and the constant multiplication is homogeneity. Similarly, we have time domain shifting property, that is xt minus t naught. So Laplace transform of xt minus t naught consists of e to the power minus st naught xs. First property this one, second property this one. Similarly, we have Laplace domain shifting. So in this we have frequency shifting. So we have to multiply e to the power s naught t xt, and the Laplace transform of this is x s minus s naught. So this is your third property, which is important property. Then time and Laplace domain scaling property, which is fourth property. So Laplace transform of x of at, this is 1 upon mod of a x of s by a. So here we are scaling. When a lies between 0 to 1, it has a expansion, and when a is greater than 1, it has a compression. Accordingly, there is a change in the frequency also. Conjugation property, that is x dot t, the Laplace transform of this is x dot, capital X dot, s dot. Time domain convolution, which is important property, sixth property. So x1t convolution x2t, and the Laplace transform of this is x1s multiplied by x2s. So convolution in one domain is multiplication in frequency domain. So here this is convolution in time domain, and this is multiplication in frequency domain. Then time domain differentiation property. So here this is sixth, seventh property. So d by dt of xt, and the Laplace transform of this is s of xs. And if there is initial conditions are there, then the values will change, minus of x of 0 negative, like this. So what we have to do, we have to see the Laplace transform domain differentiation property, which is basically minus t of xt, and this is d by ds of xs. Similarly, time domain integration property, that is from minus infinity to t, x tau d tau, and the property is basically If you see, the property is basically 1 upon s of xs. So, these are some properties of the Laplace transform which are very useful in the case of when you are doing some numerous examples or numerous questions which are of something which is not basic Laplace transform questions, but beyond that basic questions you can use properties on that complex questions, numericals. So, in the next lecture what we will discuss about the inverse Laplace transform and how to find out the inverse Laplace transform with the help of various ROC's region. We have defined ROCs in the questions. You have to, it is mentioned that for this particularly ROC regions, you have to write the Laplace inverse, the value of xt, and for that way, we have to see how we define the left half plane and the right half plane, because for the right sided signal, we have to use multiplication with ut, and for the left sided signal, we have to multiply with the u of minus t. And for that particular thing, we have to be careful while writing the expression for xt. So, we see in the next lecture how these properties and the inverse Laplace transform and the ROC regions which we have defined in this lecture is going to be useful for calculating the value of xt from xs for possible ROC's conditions. So, thank you so much. We will meet in the next lecture. These are some references. We have used the book A.V. Oppenheim, which is the basically a textbook for a particular this course, that is basic signals and system. Also, we have some reference books like R.F. Zemer, B.P. Lathi, and you can use these number of books for getting knowledge of this particular Laplace transform and ROC and how to write the inverse Laplace transform for this lecture. Thank you so much.